LCR series circuit. You have the components coming up. In real life, they will look like this. That's the inductance, the capacitance, and the resistance. But these are the circuit symbols. And then the source is an alternating source where the frequency can be changed all the way from 10 to 200 hertz, which is what we do in the lab. And then the resonant frequency is given by a 1 by 2 pi square root LC, where L and C are the values of the inductance and the capacitance. So we will first find the theoretical value of this frequency, the resonant frequency, and then we'll try to find the experimental value. Look at the Phasor diagram, which represents the currents and the voltages. We will see that the current through all the three components are the same, and the current is represented along the x-axis. The voltage in an inductance leads the current by 90 degrees. So you see the voltage is shown rotated through 90 degrees in the counterclockwise direction. So if that's the current, the voltage across the inductance is along the positive y-axis, because the voltage leads the current by 90 degrees. On the other hand, when you look at the capacitor, the voltage lags the current by 90 degrees. So that's the current, and then you rotate it in the clockwise direction through 90 degrees. So now we need to find, what about a resistance? For a resistance, the voltage and current are in phase with each other. So the current and voltage both are along the positive x-axis. So to find the resultant voltage, first we take the resultant of these two vectors, which is quite easy. Take the difference between them, okay, which is what is represented here. See, VL, VC, and VR are the voltages across those components. And then you can see that this vector represents the difference between VL and VC. And then that is VR. So to find the resultant of those two vectors, we find the value of the diagonal AB using the Pythagorean theorem. So there, AB is going to be square root of AC squared plus BC squared. Definitely can move that AC squared plus BC squared, but we know AC is I times R. So when you square both and take the square root of I squared is I, that comes out, and then you have R squared plus BC. Now BC is the same as, of course, is the same as this, which is the difference between IXL and IXC. So it's IXL minus XC, and that's why you have that in that form. And then all of this is together called Z, which is the impedance. So the value of the impedance is square root R squared plus XL minus XC whole squared. That's the value of the impedance. And remember that at the resonant frequency, XL becomes equal to XC. And so when XL becomes equal to XC, that becomes 0, so the impedance becomes a minimum. The value of the impedance just becomes equal to Z. Okay, so and Z, I mean the value of the impedance becomes equal to R. So that's why I've placed Z min is equal to R. And then you get the maximum value of the current, because when the impedance becomes minimum, the current becomes a maximum. So you get I max is V by R. Frequency of 10 hertz, the voltage is 0.449 volt. At 20 hertz, you can see the simulation working. The voltage is increased. So at 40 hertz now, you need to read the values from the lower left side for each frequency. Here is the frequency of 60 hertz. At 60 hertz, 70 hertz. Read the voltages from there where it says RMS voltage. 80 hertz. So those are the voltages across the resistance. Okay, so when we measure the voltage across the resistance, because we know the resistance is 10 ohms, and you divide it by 10, you get the current. So there it is for 110 hertz, 120 hertz. Look at the voltages where it says RMS voltage. 130, 140, now that's a simulation. See the voltage for 150, 160 now, 170, 180, and 190 hertz. Now we're going to fine tune and find the exact resonant frequency. So you see 102 hertz. I'm going to change the frequency now to 101 and look at the voltage. Next I will change it to 103. Look at the voltage. 7.07 for 103. Then I'm going to change it to 104. Here the simulation becomes a little insensitive. Again, I see it as 7.07 for 104 and 105. 105, it's kind of stuck at 7.07. So 7.06 now maybe. So we know that the resonant frequency is 104 hertz. So that's what we take. The resonant frequency of an inductance, capacitance, resistance circuit is given by the formula F is equal to 1 by 2 pi square root LC. And so when you look at those, and since we are using 0.023 henries as the inductor, and the capacitance is 10, it's 100 microfarad, which is 10 to the negative 4 farads, we calculate the resonant frequency to be 104.9 hertz. So that's the resonant frequency, the theoretical resonant frequency of this circuit. So next what we're going to do is we're going to pick a certain frequency, which could be anything, and at that frequency we will calculate the total impedance of the circuit. Now for that we'll have to calculate the inductive reactance, the capacitive reactance, and then use that to calculate the impedance. So here we go first. That's the resonant frequency. And then we're picking a frequency of 103.7 hertz, which is what I used in the simulator. And the voltage measured at the inductor was 10.74 volt. The inductive reactance is 2 pi F times L, and we know VL is I times XL because voltage is the product of current and reactance. The current is 0.707. Remember that the current through all the components are the same in a series circuit. So we got the current through the resistance, which would be the same as the current through the inductance, which is what we're using. So 2 pi times the frequency is 103.7, and we are trying to calculate the value of the inductance experimentally. So we set that equal to 10.74, and then from there we will be able to calculate the value of the inductance, which is 10.74 divided by all the other factors that go into the denominator. And once you plug all those values in, you get the inductance to be 0.0233 hertz. I mean 0.0233 Henry. Wow, which is very close to the theoretical value of 0.023. Remember, it's a simulation, that's why it comes so close. Next, we will use the measured voltage across the capacitor and then try to find the experimental value of the capacitance. Now, the voltage measured across the capacitance is given by IXC, and XC is 1 by 2 pi FC. And from there, Since the measured voltage was 10.71 volt, we will set that equal to current times XC, just like we did before. Voltage is the product of current and the reactance. And then we will calculate the value of the capacitance, which comes out to be 0.707 divided by all the other terms, 2 pi f, and the voltage. And when we do that calculation, we get the value to be 101 times 10 to the negative 6 farad, which is 101 microfarad. So that gives the value of the capacitance. So now we have the experimental value of the capacitance. Remember, the theoretical value of the capacitance was 100 microfarad, and we got really very close. We got 101 microfarad to be the. When we draw the resonant frequency curve or the frequency response curve, where you take the frequency on the x-axis and the measured current along the y-axis, this is the type of curve that we get. So we can see here that the current, as the frequency increases, the current increases, and then at a particular frequency, the current becomes a maximum. That particular frequency is called the resonant frequency. And if you keep increasing the current, then if you keep increasing the frequency, then the current decreases and goes down to a minimum. So this frequency at which the current becomes a maximum is called the resonant frequency, which we have determined from the lab. Thank you, and I hope you understood this. This is a cool lab. If we could have done it in the lab, it would have been so much better, but under these circumstances, this is the best we can do. So we looked at the resonant frequency theoretically and experimentally, and we were able to compare the two frequencies. Not only that, we could experimentally determine the value of the capacitance, the inductance, and the resistance. Thank you.